Very good morning to all of you. In today's class, I am going to explain you some more problems based on the topic mechanical properties of fluids. All these questions are given in previous JEE main, in particular from the year 2019 to 2025. Let us move on to the problems. Actually, in yesterday's class, I have completed up to 20 problems. So, let us start with 21st problem. See here, the secret of doing problems perfectly in the examination. First, you have to read the question properly, understand the content, note down the data, relevant formula and substitution, do the calculation. So, read the problem carefully. Velocity of a small ball of mass 0.3 grams and its density is 8 gram per cc dropped in a container filled with glycerin becomes constant after some time. Density of glycerin here is given as 1.3 gram per cc. So, the value of viscous force acting on the ball is x into 10 to the power of minus 4. So, a ball is dropped into glycerin and after some time that ball attains terminal velocity in glycerin. What is the viscous force acting on it? See, actually viscous force is F is equal to 6 pi eta RV, where eta is the coefficient of viscosity of the fluid in which the object is travelling, R is the radius of the object and V is the terminal velocity or constant velocity. Actually, when let us assume this is a ball dropped into a fluid, its weight mg will be acting in the downward direction and buoyant force due to the fluid will be acting in the upward direction. So, the net weight of the body will be weight minus buoyant force, that is mg into 1 minus rho by d. Okay. Now, when viscous force is like friction in case of solids, it opposes the relative motion. So, it comes into play in a direction opposite to the velocity of motion. As a result of the net force due to weight and buoyancy, the object moves down with some velocity. Then viscous force opposes its motion, so it comes into play in the upward direction. So, as it falls down, velocity increases and as per this equation, as viscous force is proportional to velocity, viscous force also increases. When it attains a particular velocity known as terminal velocity, viscous force exactly balances the net force acting on the object. So, the force acting on the object in the downward direction. So, when this viscous force exactly balances the downward force, net force on it becomes equal to 0 and then onwards the object moves with terminal velocity as its acceleration is 0. So, here this is the equation mg into 1 minus rho by d, that is weight minus buoyant force is the net downward force acting on the object. When it is balanced by the viscous force, naturally it moves with terminal velocity. Here you are supposed to find when it attains constant velocity, find the viscous force, that is nothing but mg into 1 minus rho by d. So, here just let us substitute the data given. F is equal to m, mass is given as 0.3, you have grams, you have to convert that into kg. G is 10, 1 minus rho by d. Rho is given as density of glycerin is given as 1.3 gram per cc and density of the object is given as 8 gram per cc. But anyway, you need not convert that gram per cc, numerator and denominator, it gets cancelled. So, here viscous force is equal to 0.3 into 10 power minus 3 into 10 is 10 power minus 2, 8 minus 1.3 by 8. So this is 0.3 into 10 to the power of minus 2. 8 minus 1.3 is 6.7 by 8. So if you simplify that, you will be getting it as 25. So here, okay, 25 into 10 to the power of minus 4. That is the answer. If you simplify this, you get it as 25 into 10 to the power of minus 4. It is given as x into 10 to the power of minus 4 Newton. So x value is 25 in this problem. So you have to simplify the calculation carefully. Okay, move on to the next problem. Look here, a hydraulic press can lift 100 kg when a mass m is placed on the smaller piston. It can lift how many kg when the diameter of the larger piston is increased by 7 times and that of the smaller piston is decreased by 4 times, keeping the mass constant on the smaller piston. So let us try to understand the concept or working of hydraulic piston. So this hydraulic pump has 2 arms very obviously. One is the narrower tube arm and the other one is the wider arm. So here let the narrow arm area be A1 and the force applied on that piston is F1. On this, which is at the same, so a fluid is filled and it is being communicated. So the level will exactly be the same. And here the area of the wider arm is A2, so upthrust created will be F2. From Pascal's law, when in a continuous liquid at the same level, pressures are equal. Here the pressure is F1 by A1, that is equal to F2 by A2. That is the principle of hydraulic lift. F1 by A1, pressure at both narrower and wider pistons will exactly be the same because they will be at the same level as the liquid is communicated in both the limbs. That is the concept. Now here, so F2 is equal to F1 by A1 or A2 by A1 into F1. In this problem, look here, initially some mass is placed on the narrower piston, so lifting capability is given. Without changing the mass on the narrower piston, the diameters of the 2 tubes are changed. So what will be the lifting capability now? That is the question. So in this data, as he didn't change the load kept on the narrower one, F1 is constant. So F2, that is the lifting capability in the second case, is directly proportional to A2 by A1. Now look into the data. The diameter of the larger is increased by 4 times. If the diameter is increased by 4 times, radius also gets 4 times. So area becomes R square, that is 16 times. So A2 dash becomes 16 times its initial and that of the smaller piston is decreased by 4 times. So if the diameter decreases by 4 times, radius becomes 1/4, area becomes 1 by 16th. So let us substitute these things given in this. This area is made 16 times. So F2 is equal to A2 is made 16 times the initial, A1 is made 1 by 16 times the initial into F1. That is the original lifting capability is 100 kg. So from this F2 is equal to 16 square is 256, 25600 kg. That is the answer. So the answer is 25600 kg. That is the numerical problem, integer type of problem given. Move on to the next one. Look here. A solid steel ball of diameter acquired a terminal velocity while falling under gravity in an oil of density and density of steel is also given, the coefficient of viscosity of the oil. See here, we have seen the explanation for this kind of problem previously. So here that is mg into 1 minus rho by d is equal to 6 pi eta Rv. As the what is asked, coefficient of viscosity is asked. So eta is asked here. So mass of the object dropped into the fluid will be volume into density, that is 4 by 3 pi r cube dg 1 minus rho by d. Rho is the density of the fluid, d is the density of the object which is dropped into the fluid. So this is 4 by 3 pi r cube dg. If you take LCM, d minus rho by d, that is equal to 6 pi eta Rv. So this d gets cancelled, this r gets cancelled, r square times pi and pi gets cancelled, 2 gets cancelled 3 times, 2 times. So here we want to find eta. So eta is equal to 2 r square g d minus rho by 3 into 3, 2 by 9 r square g d minus rho. You have to bring this to this side, it becomes divided by v. Just you need to substitute the given values, 2 by 9. Now what is r value given? 3.6 millimeters is the diameter, radius is 1.8 millimeters. So r square 1.8 into 10 to the power of minus 3 whole square, and g is given as 9.8 meter per second square, density 7825 minus density of the liquid is given as 925 d minus rho by terminal velocity. Look here, terminal velocity is 2.45 into 10 power minus 2. 2.45 into 10 to the power of minus 2. You can simplify that. If you simplify it, you will be getting the answer as 1.99 SI units. Okay. So everything is converted into SI system. So on simplification, we are getting the exact answer, that is 1.99 SI units. Okay. So this is the concept here. Okay. After substitution, this is the final answer. Move on to the next problem. Look here. A tube of length L is as shown in the figure. Radius of cross section at this point is R1. Velocity with which the liquid is entering is V1. Radius of cross section at the point 2 is R2 and velocity with which the liquid is coming out is V2. Suppose if water velocity at V1 is 2, what is the water velocity at the point 2? So here what are the things given? Radius R1. Look here, R1 is given as 1 centimeter. No, at the wider point, R1 is given as 2 centimeters and R2 is given as 1 centimeter. Okay, and then what else is given? Entering at the point, V1 is given as 2 meter per second. Suppose to find velocity V2. V2 is how much? So here this is based on equation of continuity. In streamline flow, equation of continuity says volume rate of flow of liquid is constant. Volume rate is A into velocity is volume rate. So in this volume rate is constant implies A1 V1 is equal to A2 V2, from which V2 is equal to A1 by A2 into V1, A1 by A2 into V1. So V2 is equal to R1 by R2 because A is proportional to R square. So V2 is equal to R1 by R2 whole square V1. R1 is 2, R2 is 1. So, it becomes 2 by 1 whole square into V1 is given as 2 meter per second. So, 2 2s are 4, 4 2s are 8. So, it is 8 meter per second. So, this is based on equation of continuity, that is in streamline flow, volume rate of flow of liquid is constant, that is the product of area of cross section and velocity of the fluid flow remains constant. AV is constant. If it becomes narrower, velocity will be more and vice versa. Okay, move on to the next problem. Look here. Look here carefully. This is a statement question. In the experiment for the measurement of viscosity of a given liquid with a ball having radius r, consider the following statements. Graph between terminal velocity and radius. So, first of all, we should know the relation between terminal velocity and the radius. Already we have seen this formula, mg into 1 minus rho by d is 6 pi eta rv, where v is the terminal velocity, from which on simplification we got it as 4 by 3 pi r square g d minus rho is 6 pi eta rv. Here, if you round off the constant factors, see here, terminal velocity is proportional to r square. So, very obviously, if we draw a graph between, if y is proportional to x square, the graph drawn between x and y is a parabola. We know it pretty much well. So, here exactly on the same basis, if you draw a graph between velocity and the radius, it is going to be a parabola. So, that is a correct statement. Next statement, the terminal velocities of different balls are constant for a given liquid, which is not true, because terminal velocity depends on the radius and diameter or size of the ball. So, that is a wrong statement. Measurement of terminal velocity depends on temperature, because coefficient of viscosity of the fluid changes with temperature. In case of gases, coefficient of viscosity increases with temperature. In case of liquids, coefficient of viscosity decreases with temperature. As coefficient of viscosity changes with temperature, the measurement of measurement of terminal velocity depends on the temperature. That is a correct statement. Experiment can be utilized to assess the density of the liquid. Very obviously, density of the liquid can be measured if eta of the liquid is already known. So, A, C, D are correct and B is wrong. And balls are dropped with some initial speed, value of eta changes. That is what given. Balls are dropped with some initial speed, eta value changes. No. Eta is constant, that is a characteristic feature of the given liquid. It does not depend on the object which is dropped or the velocity of the object and so on. So, that is a wrong statement. So, B, A, C, D are true. Okay. Now, this is also, look here, water flows in a horizontal pipe whose end is closed with a valve. The reading of the pressure gauge attached to the pipe is P1, reading of the pressure gauge falls to P2 when the valve is open. What is the speed coming out of the pipe? See here, when the valve is closed, the pressure is P1. When the valve is open, the pressure falls to P2. From Bernoulli's theorem, lost pressure energy will be converted into kinetic energy, from which P1 minus P2 is equal to half rho V square. So, here as the same liquid is considered, half rho is constant. So, velocity with which water comes out of the pipe when the valve is opened is proportional to P1 minus P2. P1 is the pressure measured with the gauge when the valve is open. P2 is the pressure measured when the valve is open. So, P1 minus P2 is half rho V square, which says V proportional to root of P1 minus P2. Fourth option is true. Again, 27th. A small rigid spherical ball of mass m is dropped in a long vertical tube containing glycerin. The velocity of ball becomes constant, that means it attains terminal velocity after some time. If the density of glycerin is half the density of the ball, viscous force. See, here we have seen so many problems already on this. mg into 1 minus rho by d is equal to F. mg is the weight of the ball dropped into the liquid, rho is the density of the liquid, d is the density of the object. In this, he mentioned that density of glycerin is half the density of the ball. So, d by rho is equal to, or rho by d is equal to half. So, mg into 1 minus half is viscous force, or viscous force is just equal to mg by 2. That is the answer. Bernoulli's equation. See here, in your textbook, this is a common diagram we have when we are deriving Bernoulli's theorem and all those things. So, Bernoulli's theorem is nothing but it is based on law of conservation of energy in case of fluid flow. So, fluid has three kinds of mechanical energies: potential energy, kinetic energy, pressure energy. Okay, potential energy of in streamline flow, the total energy remains constant. Potential energy plus kinetic energy plus pressure energy remains constant. Potential energy is mgh, pressure energy is pressure into volume of the liquid flowing, kinetic energy is half mv square. So, Bernoulli's theorem states that when a liquid is flowing through a tube of irregular cross section at different levels, so whatever it may be, in streamline flow, the total energy of the liquid remains constant. That is mgh plus pv plus half mv square is constant. That is a total energy per unit volume. If you consider total energy per unit volume, it becomes mass by volume, this by volume, mass by volume. Mass by volume is nothing but density of the fluid, rho gh plus v and v gets cancelled here, pressure plus mass by volume is rho, that is density, v is the velocity here. So, that is the commonest form of Bernoulli's theorem we use while solving the problems. That is rho gh plus p plus half rho v square is constant. So, here exactly this is the expression where the symbols have their own meaning. That is a very important question, we know, Bernoulli's theorem. Now, look into the next problem. Look here, again a statement question. Given below are two statements. Statement 1, viscosity of gases is greater than that of the liquids. No. Viscosity of gases is less than that of the liquids. Okay, so viscosity of gases is less than that of the liquids, but have, as he mentioned, greater, very obviously that is a wrong statement. Now, surface tension of a liquid decreases due to the presence of insoluble impurities. That we know pretty much well. See here, to eradicate the mosquito breed in water ponds, in stagnant water ponds, they spray kerosene oil. So, kerosene becomes an impurity which is not dissolvable in water. So, when insoluble impurities are added to water or any liquid, its surface tension decreases. So, because of that reason, mosquito breed is eradicated on stagnant water, right. So, here surface tension, the two important points here we are going to learn is surface tension of a liquid decreases as temperature increases, it decreases as insoluble impurities are added. So, here statement 2, what is given? Surface tension of a liquid decreases due to the presence of insoluble, this is a right statement. So, 1 is incorrect and 2 is correct, this is the right option. See, just another thing we should learn is, in case of gases, coefficient of viscosity increases as temperature increases, and in case of liquids, it decreases as temperature increases. Okay, move on to this next problem. 8 equal drops of water are falling through air with steady speed. If the drops coalesce, what is the new steady speed? Steady speed means terminal velocity. See here again, mg is equal to 6 pi eta rv, from which we have already proved terminal velocity is proportional to r square, where r is the radius of the drop. We know mass is equal to volume into density, as density of the given drop is mass is proportional to volume. So, m proportional to r cube, which in turn says r proportional to m to the power of 1 by 3. Okay, so v proportional to, look here. So, let me write v proportional to r square, r cube proportional to mass. So, r proportional to m to the power of 1 by 3, r square proportional to m to the power of 1 by 3. When 8 drops coalesce, mass becomes 8 times. So, when n drops coalesce, mass becomes n times. So, here radius is proportional to n to the power of 1 by 3, r square becomes n to the power of, see, r square becomes n to the power of 2 by 3 or n to the power of 2 by 3. Okay, actually by this time this is very simple, r square proportional to m to the power of 2 by 3, mass proportional to number of droplets coalesced. So, v proportional to n to the power of 2 by 3. So, here how many drops coalesced? 8 drops are coalesced here. So, r, then terminal velocity of the big drop will be 8 to the power of, as terminal velocity, this implies terminal velocity is proportional to n to the power of 2 by 3. So, V2 is equal to 8 to the power of 2 by 3 times V1. 8 to the power of 2 by 3 is 4 and V1 is given as 10 centimeters per second. 4 tens are 40. So, 40 centimeter per second, that is the right choice. See here. So, I am telling, actually you need not even put the pen on the paper, straight away you can answer. 8 drops are coalesced. V is proportional to n to the power of 2 by 3 times initial. Cube root of 8 is 2, 2 square is 4, 4 times the initial. Initial is 10, answer is 40. Understood? Move on to the next problem. Look here, again hydraulic pressure pump. So, a hydraulic automobile lift is designed to lift vehicle of mass 5000 kg. Area of cross section of the cylinder carrying the load is 250, maximum pressure on the smaller. So, here again from Pascal's law, pressures at these two levels are equal. So, pressure exerted on the smaller is exactly equal to the pressure exerted on the wider one, which is supporting the load. So, here load is given as 5000 and area of wider one is given as 250 centimeter square. As pressures are equal, we can say P1, pressure on the narrower one applied is load it has to lift up and the area of the wider tube, mg by A2. So, P1 is equal to, what is m here? 5000 and g, let us take it as 10 by area. Area is given as 250 centimeter square. So, 250 centimeter square when converted into meter square becomes 10 to the power of minus 4. So, here 250 gets cancelled 20 times. So, it is 2 into 10 to the power of 6 pascals. That is the answer we got. So, it is 2 into 10 to the power of 6 pascals. Move on to the next problem. Look here. A small ball of mass m density rho is dropped in a liquid of density rho naught. After what is the viscous force? That is the straight formula which we have done so many problems on that. Viscous force should balance the net downward force acting on the object. So, it is mg minus buoyant force, mg into 1 minus density of the liquid. Rho naught by density of the object is given as a rho. So, this is the right choice for that problem. Move on to the next problem. A water drop of radius 1 micrometers falls in a situation where the effect of buoyant force is negligible. Buoyancy is neglected here. So, viscosity of air is given and density of air is negligible as compared to that of water. Terminal velocity. So, mg into 1 minus rho by d, as density or buoyant force is neglected, mg is equal to 6 pi eta r v. So, v is equal to mg by 6 pi eta r. Mass is equal to volume into density 4 by 3 pi r cube d g by 6 pi eta r, from which the terminal velocity is 2 by 9 r square dg by eta. So, just to substitute the data. So, it is 2 by 9. Radius of the drop is given as 1 micrometer. Micrometer is 10 to the power of minus 6. R square becomes 10 to the power of minus 12. And density is given as, what is the density? It is a water drop. So, water drop density is 10 cube and g is given as 10 meter per second square, and eta is given as 1.8 into 10 to the power of minus 5. On simplification, we are getting it as 123.4 into 10 power minus 6 meter per second. So, complete the calculation. You are getting exactly the answer given, that is 123.4 into 10 power minus 6 meter per second. So, here as the buoyant force is considered, we have just taken mg is equal to 6 pi eta rv, where m is 4 by 3 pi r cube into density of the object. That is it. Now, look here, terminal velocity of a drop depends on the radius, as we have derived it already. Terminal velocity is proportional to r square. That is the reason why the graph drawn between terminal velocity and radius is a parabola, given in the statement question. There I explained you. Now, move on to this. A raindrop falls from a height above the ground. Assume that the drop is spherical throughout its fall and the force of buoyancy is neglected. The terminal speed attained by the drop. You are supposed to find the terminal speed. So, here once again, see 4 by 3 pi r cube d minus rho g is 6 pi eta r v. Actually, he said the force of buoyancy can be neglected. So, if you neglect the force of buoyancy, it just becomes 4 by 3 pi r cube dg is equal to 6 pi eta r v, from which v is equal to 2 by 9 r square dg by eta. So, on substituting all the values, 2 by 9, radius is given as 0.2 millimeters, 0.2 into 10 power minus 3, that is 2 into 10 power minus 4 whole square. So, this is 4 into 10 power minus 8, density is 10 cube and g is 10, divided by eta is given as 1.8 into 10 power minus 5. On simplification, we got it as 4.94 meters per second. That is the answer. So, here if buoyancy is neglected, we get it as 2 by 9 r square dg by eta is the terminal velocity. Just we have substituted the data given. Move on to the next problem. Look here. Height of a cylindrical vessel kept on a horizontal surface. A is the area, base area of the vessel, and it has a small hole here, and its area is small e, made just at the bottom side. the minimum coefficient of friction necessary to prevent sliding the vessel due to the impact of the force. It's a beautiful problem covering so many concepts. See here, in laws of motion, when water is ejected out of a hole, the force with which it comes out is AV square rho, isn't it? When a water jet is ejected out of a hose pipe, the force with which it comes out is AV square rho. So, that is the force with which water jet is ejected out of this. So, as a result, when it is a rocket principle or from law of conservation of momentum, as a water jet is ejected with this force, that is third law, Newton's third law, it exerts a reaction on the vessel. So, it exerts the same force in the opposite direction. As a result, there will be a tendency for the vessel to slide back. Whenever there is a relative motion between the two surfaces, friction comes into play and tries to oppose the relative motion. So, that friction, if the friction is sufficient, that vessel will not slide back. So, the frictional force should balance the force exerted by the water jet on the vessel in the backward direction. So, friction on a horizontal rough surface is mu mg, where mg is a normal reaction or weight supported by that surface, right. So, here the force, the concept is, look here, the water jet is ejected out with a force AV square rho, where A is the area of the hole through which it is coming out. So, as it comes out with the force, it exerts reaction on the vessel, that is in the backward direction. To stop sliding the vessel, friction comes into play in the opposite direction. If friction balances this force, then it won't slide. So, if F is equal to F, the cylindrical vessel doesn't slide. What is F? F is the frictional force mu into mg. M is volume into density. Volume is area of cross section, height of the liquid column into density of the liquid G. That is equal to F. F is equal to AV square rho. F is equal to AV square rho. But velocity with which the liquid comes out through this hole is equal to root 2 GH. So, A V square is 2 GH rho. So, if you balance these two, mu A H rho G is equal to A V square rho. So, here let us cancel H rho G gets cancelled, mu is equal to 2A by capital A, that is the answer. Okay. So, here water jet is ejected out of a hole, then it is ejected with a force AV square rho, where A is the velocity of the hole through which it is coming out. Here the hole is made here, it is coming out of the hole with that force. So, the reactional force developed on this is the same, that is AV square rho, that is being balanced by the friction, then that cylindrical vessel does not slide back. Okay. Move on to the next problem. An ideal fluid flows through laminar flow, a streamline flow, through a pipe of non-uniform diameter. Maximum and minimum diameters are given, ratio of minimum maximum speeds. It is simple. In laminar flow, as per the equation of continuity, volume rate of flow is constant. Volume rate is AV is constant, A proportional to R square V is constant, isn't it? R square V is constant, hence V is inversely proportional to R square. So, V minimum by V maximum will be minimum radius by maximum radius whole square, that is 4.8 by 6.4 whole square. So, if you cancel 1.6 here, this is 3 by 4 whole square, or it is 9 by 16. This is the correct option for that problem. Just simple problem, that is IPA level problem given in previous JEE main. Now, 30th. A solid sphere of radius r requires terminal velocity V1 when falling through a viscous fluid of coefficient of viscosity eta. It is broken into 27 droplets and all the droplets are falling through the same liquid, then the terminal velocity of each droplet is given as V2, what is V1 by V2. And previously, just now in this session only, we derived the terminal velocity is proportional to r square, which in turn proportional to m to the power of 2 by 3, which in turn proportional to n to the power of 2 by 3. Terminal velocity is directly proportional to n to the power of 2 by 3. Here the big drop splits into n droplets. So, velocity of the droplet V2 is equal to, it splits into 27 droplets. So, 1 by 27 to the power of 2 by 3 V1, 27 cube root is 3 square, 3 square is 9. So, 1 by 9 times V1. So, V1 by V2 is equal to 9. Okay? Now, so it is simple. Big drop has greater terminal velocity, small drop has lesser terminal velocity, as terminal velocity is proportional to r square. And r to the power of 2 by terminal velocity is proportional to r to the power of 2 by 3. And r to the power of 2 by 3 is proportional to n to the power of 2 by 3. That's it. Okay. Move on to the next problem. Water flows into a large tank with a flat bottom at the rate of 10 to the power of minus 4 meter per second. So, the rate at which water is falling is 10 to the power of minus 4 meter cube per second, that is AV rho. Okay. Now, see A1 V1 rho 1 is also given. So, rho is 1 gram per cc. So, AV1 is okay. So, here let me complain. Look here. So, mass rate is given as 10 to the power of minus 4 meter cube per second. So, here this is 10 to the power of minus 4 is AV1 rho. Area of cross section is given as 1 centimeter square. Height remains constant. Height remains constant when AV1 rho is equal to AV2 rho. This and this finally gets cancelled. So, that implies 10 to the power of minus 4 must be equal to area of cross section into area of cross section of the whole made into velocity. Velocity is square root of 2gh. So, 10 to the power of 4 and 10 to the power of 4 gets cancelled. Square root of 2gh is equal to 1, or h is equal to 1 by 20, or it is 5 into 10 power minus 2 approx. Or if you take that g as 9.8, because they didn't give g as 10, just for simple calculation I have taken it as 10. If you take it as 9, you will be getting it as 1 by 19.6 and it will be 5.1 centimeters. Okay. So, you got it as 5 into 10 power minus 2 meters. So, if you 10 power minus 2 meters is 1 centimeter. So, it is 5 centimeters. Next problem. Look here. Read the problem very carefully. Consider a completely full cylindrical water tank of height 1.6. The total height up to which water is taken in the tank is 1.6 meters. Cross sectional area of this is given as 0.5 meter per second square. It has a small hole of 90 centimeter square. It has a small hole on its side at a height of 90 centimeters. If 90 centimeters is converted into meters, it is 0.9 meters. So, it has a hole at a height of 0.9 from the bottom. So, from the top end it is at a distance 0.7 meters. Now, a load of 50 kg is applied on the top surface of water. With what velocity it comes out? It is truly based on Bernoulli's theorem. So, Bernoulli's theorem is P1 minus P2 is half rho V square. Suppose if you apply Bernoulli's theorem across this, atmospheric pressure is same in both cases. So, when we are taking the pressure difference across the whole P0 gets cancelled. So, what is the additional pressure here the liquid experiencing is, one is due to the liquid column and an additional load is placed on the top surface of the liquid. So, here the excess pressure at the inner side of the hole is mg by A, where mg is the weight kept on this and A is the area of cross section of that liquid surface. mg by A plus h rho g is equal to half rho v square. Mass kept on, look here what is given, a load of 50 kg is applied at the top surface of water. So, 50 into g by area of cross section is given as 0.5 meter per second square. Area of cross section of the vessel or base area is given as 0.5 plus height. Height is height of the liquid column which is creating pressure at the level of the hole. That is, the total height is given as 1.6, height of the hole from the bottom is given as 0.9. So, the height of the water level above the hole is 1.6 minus 0.9, that is 0.7 meters. So, h rho g, h is 0.7, rho is 10 power 3 into g is 10. So, 0.7 into 10 to the power of 4, half rho 1000 by 2, that is 500 v square. From which here on simplification, see here this gets cancelled 100 times. So, 0.7 into this, so this is 1000 plus 0.7 into 10 power 4, 7000 is 500 v square, from which v square is equal to 8000 by 500 under root. So, 16 under root, it is 4 meter per second. That is exactly the answer. So, I will stop here for today. I will continue with some more problems in tomorrow's class. Stay tuned. Thank you and bye-bye.